Okay. I should start with one disclaimer and one putting the blame on people. Is that it was not my idea to give two successive talks in this program to this morning and tomorrow morning.
Yeah, which was
this is the talk that I sort of wanted to give. I'm going to show you a version of a colloquium talk that I've given on the subject. And it's I've often said it's a heretical subject, but I realize that what I'm really being is quixotic. Does everybody know what that means? You know, Don Quixote tilted at windmills and attacking impossible things. And it's really Sid Yip's fault. that Sid is pushing not me but us, I think, to be completely quixotic. I don't know which of us is the insane Don Quixote and which is Sancho Panza. But it's what? In any case, but these two talks are actually closely related. Tomorrow I'm going to talk about some dislocation theories that are really equally heretical. And you'll see what I mean. But they're related. There's some related ideas. And in fact, some of the same pictures that I'll show today will show up in a different way tomorrow. But what I want to do is to give a sort of a sermon to urge people to focus on simple, realistic models of systems that form glasses. I'm thinking mostly about the liquid phases. As you cool it, we'll see. I'll show you exactly what I mean in a minute about that, about glass forming. I think that this is perhaps the most beautiful fundamental problem that I know of, certainly in non-quantum physics today. And I find it very frustrating that there are so many completely different ideas about it, and that we're having trouble coming to grips with what's really going on in glass formation. So this is my way of trying to introduce a few ideas that might push people to thinking in different directions. I'm going to focus on recent numerical simulations, especially those of Tanaka, although in fact I will have something to say about complementary ideas by Emanuela Delgato, but I won't. They're behind the scenes for the most part in this. But what these computer simulations imply, is this working? Is that there's, at least for some class of glass-forming materials, there's some sort of Ising-like universality for them. And the question is that true?
For the dynamic of transition?
Yeah. I mean, I'm going to talk about equilibrium states today. Tomorrow I'll talk about driven material. What? Supercooled state. Yeah. There seems to be some kind of universality. I think it's a big question: is there at all? If so, what is the extent of it? And of course, if that's true, why? Why should that be? And so what I've been puzzled about for the last year or so is, how do you get some idea about why it might happen within a theory that is more or less realistic? Now, let's talk first about, I just want to identify for you what I call the time scale problem. And you'll see this picture a lot of the time in many different places. This is the viscosity of vitroloi. And we've seen, I think Wendy was showing us vitroloi just yesterday. And the log of the viscosity is on the vertical axis. And you see it goes from, it goes from a scale, if you think about it in time scales, as if the viscosity is just some stress multiplied by some time scale. You're going all the way from picoseconds here to days. In other words, these are really microscopic time scales, and these are time scales that really test the attention span of graduate students, to say nothing of their professors. And that makes a big difficulty, because that's the essence of why it has been so hard to really figure out what's going on here. Now, there are lots of different time scales that people talk about, and one of the things I want to emphasize is that they're not all the same. They may be closely related, but they're not exactly the same. For example, I've already pointed out that there's a viscosity, which looks like it's measuring a time scale. There's a diffusion constant, which looks like it's measuring a rate with the inverse of that time scale. There's an approximation, it's mostly a data fitting approximation by Vogel, Fulcher, Taman, that I'll come back to because it's intriguing, and it tells me that time scale has this enormously rapid variation, like what you saw for the viscosity, which is an exponent of something that diverges inversely proportional to the temperature minus,
Are you assuming at that point that at least the first two tau alphas are identical?
No. Okay. That's what these question marks mean. Okay? But I'm going to try to choose a particular definition of a tau alpha, and then in other work that I won't tell you much about, relate them to the viscosity and the diffusion constant. But you see, already you know they're not the same, because if I multiply this by that, I get a constant, and that's the Stokes-Einstein relation, which we know is violated by factors of 100 or 1,000 or more when you get close to the glass transition. Okay? So that's a very important point you make. And my point is here that a sharper definition of tau alpha, or a sharper choice of definitions of tau alpha, I think has to be based directly on motions of particles. I want to look inside the materials and see what's going on and what time scales are actually relevant. Now, here's let me show this movie. I think it just gives
That has been sort of done in colloidal glasses, Jim, right? By looking at the distribution of velocity.
Look, there's lots of
dynamical heterogeneities. Those are.
Yeah, you see,
I'm
this
just trying to say that the time scale you pick up in dynamical heterogeneities is based on motion of particles.
Yeah. No, but there are other time scales that are based on other ways of looking at motions of particles. All right?
Sure.
Okay. This is why, I really, I don't know, I enjoy giving a talk like this and having Bulbul give me a hard time. But you'll understand that's why I also enjoy sitting in one of Bulbul's talks and giving her a hard time. And I hope that Bulbul...
Tau alpha is a theoretical theorist's thing. It's not measured.
David, the question is, I'm going to talk about in a minute just which measurement of tau alpha I would like to use.
But you're defining one time scale. Well, I guess what I'm trying to say is if I look at one particular very well-defined correlation function, I can look at time scales extracted from that and see how it behaves.
And the question is that relevant to some other observation and finding another time scale?
Okay, we could ask that, but we could also ask, does something happen to that time scale as you approach?
Yeah, of course, and that's what the clear example of the violation of the Stokes-Einstein relation illustrates, among many other such situations. Let me, just to make sure that we understand what we're talking about, this is a movie of that's a binary glass coming from Andrew Liu's lab. It's an old movie. It's a relatively high temperature. It's not being sheared, however. You're just seeing the thermal fluctuations. And if you stare at this long enough, what you'll find is that most of these particles, although they're jiggling all over the place, they're pretty much staying in their with their surroundings. Then occasionally, what will happen is that one of these particles will jiggle out of its surroundings and or out of its cage, so to speak, and make its way to some other place in the system. And there's a time scale that I think is an important one, is the time scale for that sort of diffusion to happen. Here's my, I used to be an artist, but not with PowerPoint. My caricature of what goes on, I like to think of an inherent structure. Darn it. An inherent structure where the molecules have some sort of mechanically stable configurations, and then they are jiggling around those mechanically stable configurations, and that's what I wanted you to see in the movie. And then let's think about what we were seeing. What? The arrows just mean kinetic energy going back and forth. There's just they're just the.
But these aren't polarized.
No. There's nothing. These are the simplest possible disks or spheres or possibly weakly interacting elements. And then what's going to happen is that I'm going to watch the diffusion of a particle, and there's going to be some jiggling around, and it's made a jump. So there's a diffusion step in rough approximation, and then people measure these things. So you look at the R squared, and you follow different particles, and you average them, and here are at different temperatures. And at low temperatures and small times, they are just jiggling back and forth back and forth in their cages. I think I'm going to have to get an analog pointer. They're jiggling back and forth in their cages, and so that the displacement goes linearly in the time. And then there's some time when there's escaping from their cages, and then you start seeing diffusive motion where the displacements are like the square root of time. So there's a characteristic time scale at which these things change the kinds of behavior that they're undergoing. And that's one, I think that's a pretty decent definition of a tau alpha to which one could base.
The time scale of the time form.
Oh yeah, fine, good. That's in fact what's, but it's also
This
okay.
correlation function.
But it's also.
Well, I don't need a 4-point correlation function to understand that.
I understand, but the two time scales are related. Is all I'm saying.
Yeah, look, we're not there.
So
she's giving me a hard time, but she's not debating.
So
Okay.
which two timescales are we talking about here?
What?
The diffusion timescale and the viscosity timescale?
No,
I haven't talked about the
cage-breaking timescale and the chi-4 timescale. And you can also get the cage-breaking timescale without a 4-point correlation function. You can just look at a non-Gaussian parameter
Okay.
for...
The main.
Just saying the two are related.
The main
But
point
those are the two timescales we're talking about.
The main point I'm trying to make is that there are subtle and not so subtle distinctions between the ways that people think they're measuring time scales. And here, the one I actually think is probably best is if you look at this, the self-intermediate scattering function, you look at the stretched exponential behavior, and you find that has a characteristic time scale associated with that. And my guess is that that's probably as close as you're going to come to a sort of a fundamental definition of what you mean by that time scale.
But this is density correlation. What
Well,
is F?
that is a but it's a density, but it's the density at some point. It's a self-correlation. It's the Fourier transform of the density at a wavelength that's like the first peak in the scattering function.
But it's on equal times or equal?
No, that's the whole point. Is that it's the question is how it's this thing at one time times this thing at another time, and it decays. Okay.
But is it even? It's not clear. Why is it time translational invariant?
This isn't supercooled liquids.
Well, it's
equilibrium.
This is an equilibrium property.
Drawn to glasses, yeah.
There's no aging.
No. It's supercooled liquid.
It is still liquid. Okay.
Well, it's liquid, but it has come to equilibrium, and it's above the glass temperature. Everything I'm going to talk about is.
You're discussing.
I could try. Yeah.
This is following the peak of the structure factor.
Following the peak of the structure factor as a function of time.
Looking at time.
Yes. Okay.
Jim, actually, in the previous slide, the diffusion behavior that we had has a diffusion constant that is just basically radius of the particle squared divided by this tau alpha. Is that consistent?
Not exactly. Not necessarily. I think it's probably close. So the same as the one that you get here, but I'm not sure. That's not the main point of the talk. Okay. The main point of the talk is only to put this on my long list of uncertainties, all right, that I think should not be taken to be certain features of the thing. Now here's something that I think is a more controversial, and as I've told people, this is an argument that I understand every other day. And then, but there's a very interesting paper by Montanari and Semerjian. It looks as if it is indeed very mathematical. It looks as if it's talking about point to set methods. But if it's talking about point to set methods at all, it's talking about them in some very great generality. And the most interesting part of this paper, I find, is the introductory paragraph that makes the following argument, which I think is justified more rigorously by the next 20 pages of analysis. And that's that there has to be a length scale in this problem. What the length scale is, is the big question, but there has to be some length scale that's associated with these the tau alpha and the tau alpha growing.
It's slightly different, right? It says that if you have a diverging time scale, you have to have a diverging length scale.
Yeah, I'm saying that this is my common sense interpretation of the Montanari-Semerjian.
So is that a theorem?
It is a theorem. This is
you cannot get a diverging time scale without having a diverging length scale somewhere. It might not be a two-point correlation function.
Okay. Yeah. But the argument is...
Unless you have things just that.
If you have broken symmetry, for example, then you never relax to true equilibrium.
No, this is in equilibrium.
But let's think, we're talking about something. Think of these systems that I'm looking at as being basically fluid, okay?
Yes, in this particular case I agree, but it's not...
I'd like to clarify this point a little bit, because I think what Semerjian and Montanari say is that if you have a correlation length scale, right, the dependence of a relaxation time depends on that length scale within a certain inequality that they specify, that there's sort of a lower limit of how big the time scale can be, which is an algebraic dependence of the length scale, and an upper limit, which is an exponential.
Yeah. Okay, they make both limits. I'm going to focus on this one, which simply tells me that if I have sort of correlated regions with some characteristic length scale xi, then I can have independent fluctuations inside those regions, or of those regions, of the shape of those regions, or perhaps the existence. Maybe they can appear and disappear on yet another time scale that we can argue about. And what Montanari and Semerjian say is that, well, that there has to be an energy associated with that scale. And they give you a gross overestimate of what that energy is, and say that if everybody in that region was interacting with everybody else, then that energy would scale like the volume of the system, like psi to the d. But the point is that if the length scale, unless that length scale diverged, the time wouldn't diverge, and we don't know for sure whether the time is really diverging. Okay, I want to just think about this situation and say, well, I think what that means is that there has to be a length scale associated with these growing time scales. Whether they actually diverge or not is not quite to the point. And I'm going to argue that, well, it can't just be scaling with the volume of that thing, because that's not what the forces do. But there's a nice argument, which I must admit I got from a paper by Wallinus and Company, that what? The subplot of all of this is, if you read the paper that I referred to at the beginning with this key issues review, is that I don't believe Wallinus, nor do I believe a whole lot of other things that are going on in the field. But this is an idea I think is really neat, at least every other day. That if I have a region with some sort of length scale psi, and therefore it consists of psi to the d particles in some, and each one of these is making small allowable thermal fluctuations, the characteristic size of the fluctuation in this in that region is going to be Gaussian statistics. If they're making independent fluctuations, then the characteristic size of the variation is going to be the square root of n. Okay, and that's going to determine something like a fluctuation time. I'm going to argue in a minute that that's basically what that's going to determine is some sort of global frequency and attempt frequency for various kinds of events to take place. And so that
if they're correlated, which is what you presumably mean by psi, then the bestness would be a low amount.
No, you have to ask what.
It's totally random. They're not correlated.
No. If they're correlated, they're still sitting there, and their positions, at least within some sort of a interparticle length scale. But if they are correlated, that means that if they're completely uncorrelated, I can have much shorter time scales. The point is that if they are correlated, then the kind of time scale that I need it has to.
You're asking about the energy, not the just the scaling of
well,
the
but
energy.
we're going to do a.
I know, but I'm saying
we're going to do
it has to be between
estimate.
d over 2 and d, right?
Well, maybe, yeah.
D over 2 would seem to be low amount. You put nothing in it.
Well, look, you're trying to push this harder than anybody knows to push it yet. Okay. I
don't understand the squiggly.
Well, it means that, it means that I think it's going to scale like that. At least I think it's a reasonable hypothesis.
What if you just say that some exponent between d over 2 and d?
Because I want d by 2 for reasons that you'll see.
Okay.
Okay.
Jim, I mean, these fluctuations you have in any thermodynamic system, no?
Yeah.
But, okay.
Okay, but the point is that if I have correlated regions, the correlation length is going to somehow slow down the fluctuations. And here's an easy way of seeing some sort of mechanism by which that may happen.
Where does the correlation link come into that argument?
Well, if they're uncorrelated, I can have lots of much shorter fluctuations. Look, let me just go on. You'll see where it's going. You won't like it, but that's okay. Now, here's a correlation length I used to think was really a good correlation length, but Sri has talked me out of that. And it's called the dynamic correlation length. And basically what people say they're measuring, and what Sri has talked me out of is believing that that's what they're actually measuring, is a certain probability. Think about two particles sort of in their cages. And now look at tau alpha, however you want to define it later, and ask what's the probability that they're still in those cages. And that probability is going to decay exponentially, like with a correlation length that's often called xi4 because it's a 4-point correlation function. And that seems to, in some cases, be the same as the size of dynamic heterogeneities in these systems. And it is observed. What Sri has pointed out is that they're not really measuring whether they're still in their cages. They're measuring just 2-point correlations and letting. It's a 4-point correlation, I know, but the question is, they just ask, well, how long does it take for both of these guys to move a distance like proportional to the particle spacing, and they could be moving that distance without actually changing the correlations. But the question is, even assume that this is okay. Is this dynamic correlation?
Correlation function. It's a
Can we get
correlation
the
of
definition
two
on the
correlation
board, then
functions.
we can understand.
Okay. So the point is, all right. Suppose that's okay. Would this necessarily be a sign that there is some structural rigidity in the system?
So Jim, I think that the definition of the 4-point for the xi4 is not very clear to the chi. So
Can you write the definition on the board?
Well, look.
The definition.
This is the definition that is given in words. It's not what is actually calculated, and I don't want to spend a lot of time on that. Okay. I want to move a little bit faster and get into things that you'll like even less.
You look at the 2-point correlation at one time, and then you look at it at the later time, and you ask how is that?
Yeah.
What are the fluctuations in that quantity, actually? You look at, very briefly, you find the overlap of one particle with where it is at a later time. You plot that as a function of time. And then you look for many different particles, what's the variance? Where's the maximum variance in that function?
All right, now, here's the connection with Ising-like. We know that an Ising-like correlation is going to go like, well, temperature minus some critical temperature, or in this case, the difference in the volume fractions, which is the analogous controlling parameter for these liquids with a very short range of repulsion. And the Ising scaling law is that that exponent, nu, is 2 over d minus alpha, and alpha is 0 for 2 dimensions and 1/10 or something like that for 3 dimensions. So it's approximately 2 over d. If that's true, and if in fact tau alpha goes like this activated factor.
This is mean field, Jim, right?
What?
This is mean field. If it's just 2 over d, if alpha is nothing, right?
No, this is a renormalization group result. Scaling. Yeah, of course, it's scaling.
The correlation length explained?
it's approximately.
Wow.
Alpha is small, but not exactly 0.
Alpha comes out to be in 3 dimensions about 1/10. It is exactly 0 in 2 dimensions. Okay, even I know that. And if that's true, then you put those things together and you get Vogel-Fulcher. In other words, if delta E goes like xi to the d by 2, and xi goes like t minus t0 to the 2 over d, then in fact you're getting Vogel-Fulcher. At least you're in that ballpark. Yeah.
How well is it known experimentally that its exponent is 1 there?
What? Oh, well, that's, come on, that's the exact renormalization group.
No.
In the experiments.
Oh, experimentally?
The last line is that.
Oh.
Why do you say it's?
Oh, no, that's a matter of huge controversy. Come on.
Okay, so yeah, okay.
That's,
Jim,
yeah.
mean field is exact 4, not 2 alpha.
That's right. But mean field gives you d.
Mu in 2D, I think
Mean
is
field
1.
in 2D alpha equal to 2.
Nu equals.
Yeah.
Nu equals
not equal to 1 in 2D,
equal.
I think.
Alpha
Yes,
equal
it
to
is.
2.
Yeah, mu is not equal to 1 in 2D.
Yeah. Come on.
No. That's mean field.
This is hyperscaling.
Alpha.
No, it's not mean field. It's
Mu?
come on, you guys.
Beta is half. Beta is half.
Beta is half and mean
Beta is
field.
half. Mu is 1.
And mean field, but wait, look, these are.
High is, so I, yeah.
Go. Okay. So,
Alpha is 10. It's a 10 in 3D.
all right. Now here's the picture that I want you to think about. It's
Jim, I don't know. Something happened. So if it's an Ising criticality class, then the time scale should go as a power of the length scale.
No.
No?
If you're looking at critical.
If you're looking at
That's what I would mean by an Ising
this
criticality,
is
universality.
very
is the time
very
scale goes-
important that you cannot read Halpern and Hohenberg and get the Ising the Ising-like relation between length scales and time scales.
I can in an Ising.
In an Ising model, you can, yes.
So I'm trying to understand.
But
what you mean
I'm
by
not
an
saying
Ising
I'm
universality.
saying that what seems to be emerging. Look, this even emerges in random first-order transition theory. In fact, that random first-order transition theory adjusts some constants so that it gets this Ising-like scaling.
Ising-like scaling. I'm not trying to-
Just what I wrote down.
That the length scale-
The length scale goes like the temperature difference or to some power. Okay, but that's very important, Bobo, is that the results for the time scales that come out of those kinds of analysis, the dynamic renormalization group or that kinds of stuff, is very different from what happens here.
Well,
Here we get a much more rapidly
Z
diverging
equals
time.
mu.
This is like Z infinity. Dynamical exponent is infinite.
Well,
So Jim, can I just sort of try to clarify this point? I think what you're saying is that you have a length scale that's diverging as it does in
In
Ising.
2D Ising.
that's
in
right.
2D Ising.
No, in 2 or 3D Ising.
I mean, so with that squiggly,
Yeah.
he's saying it diverges like Ising in the
Yeah.
Ising universality class, but the relationship with dynamics is activated.
Yes,
It needs an explanation, which you're trying to.
that's exactly
So
right.
so these are.
Yeah.
But
because
I'm
if
still
it's-
trying to
if
understand
it's
the-
Ising dynamical, it's not the dynamics is not Ising.
The dynamics is very definitely not Ising.
Well, what's special about the Ising? Like if I had any critical point, the length scale would
Bobo,
diverge
I'm
as
trying to
time
get to the point where we're going to try to make plausible that this Ising-like scaling is a characteristic of glass-forming materials, or at least some of them. Okay, that's the main, or one of the main points that I want to make. Okay, but if I ever get there, yes. Now.
So, but in this, What is it?
Z is 0.63.
What is Z? The coordination number?
No, the dynamical exponent.
Oh,
It's infinite.
Yeah.
It's infinite. It goes exponential.
Yeah.
But how is it diverging? I mean, what does infinite mean?
It's a relation between
I know what Z is.
right.
I don't know what.
Okay.
They're related exponentially.
Yeah.
So that's
You mean the Hohenberg-Halpern Z? That's one of the most dramatic things about the glass theory is that even if you make a reasonable mean field theory and renormalize it, if you like, you get much more dramatically growing time scales than you get out of anything
So
like
isn't
that.
that the crux of the problem?
That's exactly what I said at the beginning. That's what I'm trying.
How the length scale exactly diverges as I approach this is, I don't understand where the.
Well, that's what I'm trying to get to, Bulbul.
Okay.
Okay, to give you a plausible.
But are you going to argue why the time scale goes exponentially with the length scale, or that's an assumption?
Well, I've already tried to give you via this Montanari and Semerjian idea of fluctuations, and here I'm going to say a bit more about that. Okay, is that what you need to do? You want to think about, and I'll show you a picture of some of these things in a minute. You want to think about this system with correlated regions appearing, disappearing, and you want to ask now about specific mechanisms. For example, I like the STZ creation rate or annihilation rate, which is going to be an activated mechanism. The activation energy is going to be a formation energy for the STZs.
Excuse me, what is STZ?
Yeah. Well, the local flow defects in a material.
Okay.
It's what you'd need if you were going to really make a theory of either diffusion or viscosity.
What does the acronym stand for?
It's shear transformation zones. I thought.
Could you say it's the weak spots that Karen was talking about before?
It could be, yes.
I don't know what weak spots Karen was talking about before, so let's not.
Okay.
I think
But
they're like, well, we'll get
in any case, think about, there's some
They are under shear.
there's some
These are not
defect
shear.
that is natural to the
These are not
system.
shear.
It's not built in, and it's appearing and it's disappearing. Okay, so the rate at which it's going to appear and disappear, there's going to be an activation energy, and we know very well from experiments that doesn't describe it at all. That there has to be some sort of an attempt frequency multiplying that, and it's this attempt frequency that gets very, very slow when the system becomes glassy. That's the result of a whole lot of a number of years of studying these flow defect theories. And so this is the idea that I have in my mind, is that the attempt frequency should be something like, again, the 1 over this tau alpha. It should be a global mechanism because it applies to the fluctuations of these correlated regions. And then the local creation
And that's
annihilation.
tau alpha is the one that we've been talking about so far.
It might be, yes. Okay, but in any case, this is the one that this factor gamma is going to be this e to the minus, with excited the d by 2, etc.
Can you define?
Okay.
I've heard so many different uses of STZ. Can you give me your definition of how you use it?
Yeah, that's another talk, or 3 talks. But look.
The
It
local
would really
rearrangement
help,
of
Jim,
4
because no one has
points.
given an introduction to STZ, and there are all of these terms floating around.
Okay,
There's hotspots.
Okay, I used it because I thought everybody would immediately say, "Oh yes, that's the theory I don't like," but I understand what he's saying.
Is it a local rearrangement of 4 points?
Yeah. Look, it goes back to the idea that in amorphous materials there are flow defects. Okay, a whole bunch of theories say that these are inherent to the material. Soft glassy rheology says there's some fixed population of these things. Other people do that, and that was originally Ali Argon's idea. What has he developed in the last 10 or 15 years is the important idea that you have to treat these thermodynamically, that somehow if I have a system that I'm shearing, that they have to be created and annihilated, they have to come from somewhere, and that the dynamics of the creation and annihilation is very important in order to understand the behaviors of these systems. And that's
when they're being sheared, or even when they're not being sheared?
Well, even when they're not being sheared.
So in the original picture that you showed of the simulation of part spheres,
Yeah.
where are the STCs?
Well, if you look very hard, it's a little bit too high a temperature to see that. I can show you at another talk that I can give that you can actually see that what's happening is that these things are jiggling back and forth, and every once in a while, in some localized region, you get particles rearranging.
But that's an STZ after it's flipped.
No, it's while it's flipping in that case, yeah. Look, it's a
local rearrangement of a finite number of frames.
Yeah.
Okay.
Well, I would actually put a more precise point on it, because what you see when you see the rearrangement is actually an STZ flipping. And I think there's a concept in all of these theories that there was a structural defect there before it flipped that you could see if you knew how to look for it.
If you want to use this concept, you have to be able to define it.
Okay.
Yes.
I go back in.
Show me a picture. And
I go back in my history, and I ask you: suppose you have a supercooled liquid that is possibly going to, or a supercooled vapor that is going to perform liquid drops. Okay, and that's a nucleation event. And even if you're not below the transition point, it's a fluctuation. Okay, can you look at that picture of this supercooled fluid with the fluctuation and tell me in ahead of time where that nucleation event is going to occur? Where it's going to occur and when it's going to occur? The answer is no.
Obviously not. It's equal probability.
Well, but now. And I say that the flow defect creation and annihilation and transitions are very much analogous phenomena. Okay? So this whole business, it is nice to think that you might, by catching systems in certain points, and Lisa's doing some nice things on this too, you might predict with some reasonable probability where this activated event is going to occur. But your first answer should be that in principle you shouldn't try to do that because it's a rare activated event. It has to do with rare fluctuations occurring. Okay.
What is the event?
Well, in this case, that I have a flow defect that can respond to the stress and cause a local shearing.
So if I understand Lisa correctly, you're associating a cage breaking event with STZ flipping. So can I associate the caged particle as an STZ in this case?
No.
No. Are you actually saying cage breaking is an STZ flip?
I would say that. Well, I don't know. I would say that in certainly in a sheared amorphous solid, when I have a cage breaking event, it's typically associated with as one of a group of particles that's rearranging in an STZ flip.
Look, there's another paper that I've written that says.
I would say yes. Jim apparently doesn't think so, but I would say yes.
I'm sorry. I didn't know what say. You would say what? Yes to what?
I would say that you can identify an STZ before it flips.
I say that in general, no, but maybe if you're at a low enough temperature.
Okay, I mean in the zero temperature limit.
Oh, that's a different story. Then all of my rules are off. Okay.
So Jim, are you now moving on to using the tau alpha divergence to look at something, or is the STZ an explanation of the tau alpha divergence?
I wanted this slide simply to give you an idea of how I'm thinking about these fluctuations, and that I'm thinking about the tau alpha part as being related to the attempt frequency for activated.
But this doesn't explain why tau alpha goes exponentially.
No.
So maybe let's
No, I'm still trying to understand.
Okay, what I want to do is I want to show you some numerical simulations, mostly by Hajime Tanaka and colleagues. And they've done some things that I consider, look, there are all sorts of open questions about their work. And I'm very much aware of that. But they're the first people who have done what I think of as a systematic study of a well-defined system with short-range interactions that does, in fact, undergo some kind of a glass transition. And they're the ones that first, wait a minute, I'm doing this wrong, that first showed that they were, argued, I should say, that they are getting Ising-like correlations and looking like as if what's going on as you approach a glass transition is if it is something like a critical phenomenon. And then I also wanted to make sure that everybody knows that there's this other really nice paper coming out of Zurich that does this, gets the same similar conclusion, but from an entirely different and very interesting point of view. And what there's a second paper by Tanaka and colleagues in which they've done a very interesting series of computer simulations where they looked at these two-dimensional hard disk problems at a variety of polydispersities. In other words, they're not doing the binary. Oh, they do sometimes, but what they're doing is they're increasing the internal disorder. We know that at zero polydispersity, that's a well-known, very carefully studied phase transition. That's the hexatic phase transition. We know that it comes up here. It's weakly first order, and then this is the pressure as the function of the packing fraction. And what happens is in these experiments, these numerical experiments, is that as you increase the polydispersity, you get a really pretty nice glass transition with a whole bunch of features that look as if they're coherent that occurs at these larger polydispersities. Now, here's what they're measuring in the two-dimensional systems. They're measuring this hexatic order parameter, which you just look at each particle. You compute 6i. Theta m is the angle measured relative to some orientation. So there's a hexatic order parameter, and then you look at the correlations of this order parameter. Now notice that's different from the pair correlation function. What it's doing is it's looking at correlations of local topologies. And that's where they see this kind of behavior. Now here's a picture that has a lot of things that I want you to notice about it. But this is a picture of one of their systems. The red regions, look, it's actually more interesting to look here. The redder regions are the regions of higher hexatic order. The bluer regions are the regions where the hexatic topology, local topology, is not there or is weaker.
That's the bond orientation.
That's right. And the dark spots are in fact sort of vacancies. And so that these regions are in fact somewhat less dense than those regions, as it turns out. I want you to think about this as, okay, there's sort of clusters of topologically ordered particles. These are more or less the clusters that I have in mind when I think about the Montanari-Samerjian picture. Yes, Sri?
I'm sorry, I could have asked you this before, but for the 2D hexatic ordering, is there an exponent that is known about how this length scale grows?
Oh yeah, and it does not grow. It does not grow like like side of the D. It does not look like Ising.
Oh, it does not?
No, it goes much faster than that, but very close to the transition. Okay? It's very interesting. That happens only very close to the transition, in fact,
it grows almost exponentially.
Well, it grows. Yeah, the length scale grows exponentially, and by some funny formula. But this is an exact solution by all sorts of distinguished people. I wish I had done that. But my interest here is and that's one of the things I like about Tanaka's approach, is he starts from something that he really understands, like that monodisperse hexatic system, and he sees what it's doing. He can understand, and it's a sort of a control on his simulations, and then he goes step by step away from that to see what kinds of things are happening. And I think that's a very important strategy. Whether he's right or not about this, I think that's what we need to be doing.
So the reason I asked is, do we know what the Ising so like if C6 is growing, if it is going to diverge, we should probably know whether that exponent is Ising or not.
Well, we know that at the transition it is not.
Yes.
It's different. It is in fact an exponential growth, not a power law growth. Okay.
Farther away.
Okay. Now further away, I wish somebody would measure it a little bit more carefully. Tanaka has done that a bit, but only for the more polydispersed systems. Okay. So that's what it looks. But I also want you to think about these are the correlated regions. We're in a liquid phase. They're appearing. They're disappearing. I don't really know for sure how to calculate the rate at which those are appearing and disappearing. It must have something to do with tau alpha, but you want to think about this as a fluctuating system. Okay. Now here's another picture. Here's where he's.
Jim, how close to the glass transition was that picture that you showed us before?
That picture, well, it said it's reasonably close. I'll show you.
How large is the correlation length there?
The correlation length there, where you can sort of see it here, this is a correlated region, and it looks like it's 5 or 10. What?
Are we looking at the entire system over there?
No, this is a close-up of a small piece of the system, and what you're seeing. What you're seeing is one of these correlated clusters. It's not completely correlated all the way inside, but the correlations are there. If you look carefully, you can see where it's got all sorts of defects in it. It is not a crystallite forming. It is a fluctuating correlated region. And then he compares this with basically another approach, the more dynamic approach, and he finds that the mean squared fluctuations in position are larger outside here. Those are the dynamically loose places, and these are the dynamically tight places. It's as if the regions of high propensity are these regions out there, to use Hellowell's analogy. Yeah.
So it's a global idea that the hexatic to disordered transition, it morphs into the glass transition somehow?
There is an ordering transition. The transition in the monodispersed thing, which is known, is a transition, and in fact it's a little bit more complex than that, because you first get orientational order, and then it forms sort of long-range crystalline order.
Yes, so which transition is the...
What?
It's the you're talking about the transition from no order to hexatic order, no?
Yeah.
Right. And so the idea is when you increase polydispersity, that transition becomes the glass transition?
When you increase the polydispersity enough, it looks very much like what all of us would like to call a glass transition. Okay? that's a.
And not the other transition from hexatic to crystal.
You lose the hexatic transition when you get to large enough polydispersity. I don't know to the extent to which that has been studied all that carefully as a function of where you are in the polydispersity.
Yeah, this makes sense.
I thought so.
Yeah, but I still don't know if the length scale is divergent.
Of course you don't. How are you going to?
That's I'm sorry.
Look, here's a picture you'll find in Tanaka's. He's doing too many different things, but the Xi 6, the red triangles for the two-dimensional polydispersed colloidal systems, they come along here. There may be at least a factor 5 of change in the length scale. That's a function of what he's calling T, but what T is, he explains, he really means that this is in terms of the volume fraction. But he's got all these systems, and including a three-dimensional polydispersed colloidal thing, and they line up along this line. I think he's shifted the up and down, but I don't think he's fiddled with the slopes.
Why does the 3D and the 2D have the same exponent?
Because what he's done is he's plotted as a function of this quantity to the 2 over d. Okay? So he's got both two-dimensional and three-dimensional. He's got a bunch of other models, one of which I think he needs to push even harder. It's one thing he calls a spin liquid, but where he's introduced frustration in another interesting way.
Okay, so I'm going to ask you something. So this length scale is going up by 2 orders of magnitude, right? At least 2 or 3 orders of magnitude.
No, the length scale is not.
The C?
Well, he plots here, but these are different systems along the line.
So in a particular system,
So in a particular system, I think it's about a factor 5, at most 10. Okay, but that's non-trivial because you're going to raise it to some power to get the time scale.
I know, that's why it's always a problem. Right?
Okay, but look, he's doing better than most people have done at getting the length scales like that. He does the same plot for the time scales, and I think he's got a misprint there. But this is the log of the time scale is supposed to look like psi to the d by 2. And again, these plots lie along a reasonable curve. It looks as if what he's getting for this particular system is an Ising-like behavior. Okay, I'm already over time, and I have another half of the talk in which I'd like to give you some sense of how I've been struggling with trying to figure out how to make an Ising-like field theory for this system. So let me...
Sorry, Jim.
Yeah?
The slope should be 1. It didn't look to be 1. I mean, on the slope of 2.
Look. This is a logarithm slope, but this is not.
Look,
Look, I've pored over this stuff. There are obvious places to worry, but I don't think they're really simple mistakes. So why might there be something like an Ising symmetry in this? I go back, 40 years? There's an old paper having to do with behaviors of glassy systems at low temperatures by Anderson, Halpern, and Varma. And they postulated that indeed they could understand the specific heats at low temperatures and also the thermal conductivities by postulating that there would be some kinds of states in this is a well-formed glass, that would have 2 equivalent positions. There were clusters of glassy particles that were equally happy, as they said, in 2 different orientations. Now, again, that reminds me of my shear transformation zones, which are equally happy in more or less in two different orientations, which they switch back and forth under the influence of shear, of stress. But so if most local configurations in this disordered system are rigid, and then you have occasional not so rigid places where you can move back and forth, then the most probable kinds of these flexible clusters are going to be these Anderson, Halpern, Varma sort of two-state systems.
So if I think of a system, many particle system sitting in an energy minimum,
yeah.
So one could sort of try and understand the assumption of the Anderson, Halpern, Varma theory by saying that if I were to sort of get out of the basin of an energy minimum, the lowest barrier is probably of order 1 saddle.
Yes.
Which would connect two minimum.
Yeah. That's roughly what they're saying. Yeah. Look, I prefer to say it is that 2 is the smallest integer greater than 1. Okay. that makes it.
But this is in a limit that you don't particularly fancy, which is very low temperature.
But here I'm saying I'm making roughly the same argument, and I'm talking about it in a system that is mostly rigid, because I've cooled it up. I'm close enough to a glass transition.
But then you've cooled it enough. You're close to the glass transition, or are you well below the glass transition?
Well, I want to be above the glass transition so that I can make measurements over.
But the two states aren't deep in the glass region. The Halpern and
Well, that they are, and I'm only using their idea as I say, as an inspiration. Okay.
Why don't you just keep a parameter?
What?
Make up P-state.
Well.
Keep a parameter.
Because then I
play with another parameter or determine.
Come on, that's a style of doing things that I used to love, David.
But I'm trying. Sounds gives you. I mean, there's nothing wrong with that, given the other.
As long as
2 is the first digit.
Yeah.
1.5 is next.
No, but look, and so here's one of these inherent structures, and okay, what I've jiggled things, so I think it's going back and forth, and so that hex what? I press the plot for the forward button, and I press the backward button, and I trust my my artistic ability is not good enough for you to.
But if you were in 3 dimensions.
If I were in 3 dimensions, again, 2 is the smallest integer, bigger than 1. Okay, and so the strategy that I've used, and I try to make to make a field theory out of this. And so I'm going to choose statistically relevant internal state variables, and I'm going to sort of look at populations of these 2-state clusters that might jiggle back and forth, and so and I'm going to also add a population of voids, just because I need to have, like the voids that you saw in the picture, I need to be able to vary the volume of the system, or the volume fraction. I'm going to write the volume and the entropy as functions of these variables. And then I'm just going to do, at first stage, a mean field theory. I'm going to maximize the entropy for fixed volume. The Lagrange multiplier, I know, is temperature over pressure. And I'm going to see where it takes me. And so there's some algebra.
That's when you are out of equilibrium physics, no? What you try to describe, or can you evoke?
Well, this is equilibrium.
No, he's doing it in the supercooled liquid.
I'm doing it.
He's taking the 2-state thing and saying those occur in the supercooled liquid also, which is in equilibrium.
That's why I showed you one of Andrew's pictures that was not being sheared. Okay. Bulba, you give me more hard time.
No, I'm just. I don't know what that is. I always thought there was a clear distinction between seeing the Anderson-Halpern-Verma regime, which is low temperature glass.
Yeah.
And then there is the.
Look, I'm not even sure that the Anderson-Halpern.
Which is close to the glass.
I'm not sure that even that the Anderson-Halpern-Varma picture has ever turned out to be right. And they're also okay.
I always thought it wasn't relevant close to the dynamics of
Well,
glass.
and I'm telling you that I'm using the same idea, and because to give me some guess about what the relevant internal variables are in this system. Okay. And so all I'm going to do is I'm going to put here the number of plus minus two-state clusters. I'm going to have the total number of those two-state clusters, which I'll call n star, and then there are going to be a number of voids. And now I'm going to write the volume, and the volume has certain obvious terms, but the most important thing is that these clusters reduce the volume if they're oriented parallel to each other, and they have a larger, implicitly they have a larger volume if they're.
So there should be large volume fluctuations in a supercooled liquid when I approach the glass transition?
I didn't say that. I said that, but that the volume is the control variable. Okay? And so I'm going to say that, in fact, I'm going to say that I'm going to look at a fixed volume, and I'm going to vary the values of these parameters subject to the volume being fixed and optimize the entropy to find a state.
Okay, Jim, I think here's a question that I had when I first read this work way back when I was doing something relevant that you might be talking about next week. So what is the origin of that denominator n star plus n naught?
Oh, that's just the total number of. I have to normalize this.
Yeah, I know you have to normalize so that it scales as n.
Well, but look, this is. Look, if I have to make n plus over this thing equal to a density, and now I want to have that density squared, but I've multiplied it. Look, I think after this many years, I know you don't trust me to get my algebra right, but I think I got this. What Charles has experience.
It's not a matter of algebra, but I mean by choosing this normalization, I think you're implicitly implying that the total number of sites is n star plus n0. So
that's right.
So you're implicitly assuming that that each site must either be a cluster or a void.
Look, I'm making a very sort of ambiguous definition of what I mean by voids. I do it so that I can say that I have some sort of a conservation of volume rule. Okay? And now I just ran through some algebra that I look at. This is sort of analogous to a magnetization. The eta is a number that when the number of voids goes to 0, it goes to 1. It gets very small when almost everything is a void. And I turn the volume expression into something with
it's like a spin one-izing, correct?
What's the state?
I can think of it as a spin one-izing. I have plus minus and 0.
No, it's a little bit more like a dilutizing model.
Okay.
And so I have this coupling. And 1 plus m squared is that coupling term. And then I have to write the entropy. I know what the entropy is for the two-state systems. I have to be a little bit more careful about the entropy for this eta variable. But it turns out it's not very important what you do. You want it to look sort of like an ideal gas at small values of eta, and somehow you get. I still think of it as being jammed, but I don't want to use that word in the current company.
So when you say it's a dilutizing, you mean that the voids actually remain voids; they don't change into n plus and n minus.
That's right.
Okay, and n plus and n minus can switch between each other.
Yes. But in fact, as I change the pressure or the volume, I can change the ratio. In other words, eta becomes a variable.
Okay.
Okay. And so if I do the mean field on this, I get the standard Curie-Weiss rule for the magnetization. Then I have a variation with respect to eta. It gives me a sort of interesting expression for the pressure. Theta is kT. And I've done something here because I needed to, because it turns out that it's important to understand the higher density behaviors, is that I used the fact that I'm talking about an Ising model that has a magnetization which has a beta index. But that is a somewhat less important part. Now here's the data of Tanaka and company, and this is for this is the pure hexatic thing with zero polydispersity. Then these are small polydispersities there, and then here's the polydispersity for which I showed you the picture that has that's about 9%.
Wait, I thought the different curves were different polydispersities.
They are. Okay. So but they all sort of come up here and break off. Mm-hmm. You can even see that there's a sort of a dip in there, which means that you've done violence to a first-order phase transition in there. And then these things break off in there, and finally, and here you can't actually see the break off, but when you look at it and look at the correlation links and look at the time scales associated with it, what you see is that that's where you're getting things that look very much like glassy behavior, the kind that I was showing you before. And
how long is the time scale at that packing fraction at that polydispersity? How long is the time scale?
Well, we could go back and look at those graphs, but it's the graphs that I showed you before that showed the Ising-like behavior were all at this, for this particular model, we're all at this 9%. Okay? And the point is that if you start pushing it beyond there, the theory says that the inverse fragility, the quantity that comes in the Vogel-Fulcher law, actually increases with increasing polydispersity, and it increases with as you get up to critical packing fractions. That behavior holds together in this theory, and my opinion is that the theory is obviously got all kinds of weak spots in it, but it's not so dumb that it doesn't deserve to be tested. What? Yes, of course.
It's telling you the pressure.
In this case, I've computed the pressure. Yeah.
And you can compute the timescales?
Yeah, just by putting it in that the formulas that I showed you.
Where's the comparison to the theory?
What?
Where's the comparison to the theory?
The lines here are my theoretical curves for the pressure. Yeah. And,
no, I don't understand. So you're saying that you take the theory, which is for a static correlation leg, for in an Ising model, and you're just going to assume that the time scales exponentially.
Well, that's what my theory does, and it agrees with Tanaka's experiments.
But then how does it tell me anything about the glass transition?
What do you mean?
Where the challenge is to understand why the time scale is going up as fast.
Well, that's the theory says it does. But the theory says that the time scale goes exponentially, like my theory.
That's what I'm trying to. So, how does your field theory lead to the time scale diverging exponentially, the z being infinite, as we keep saying? So, if I build up an Ising field theory, z is not going to be infinite.
Look, I've already. This is going past that. This is I've already shown you, a theoretical idea about how the time scales can grow very fast if they look like.
What is that theoretical idea? I guess
that's the time scale should go with the xi to the d by 2. All right.
That's an assumption.
Yeah. I think.
That is an assumption.
No,
right?
come on.
It doesn't come out of your field theory. There's no dynamic field.
The field theory is built on that kind of an assumption, right?
No, I don't see any
Field
trying
theory,
to
I'm
say
sorry,
the
the field
theory.
theory.
The field theory.
Well,
The field theory is for the equilibrium.
Look, the field theory.
No time scale on it.
The field theory is that's right. I've not tried to make a time-dependent field theory there.
I think what she's saying is there are two separate parts to this theory.
Right.
Yes.
And here you're talking about a simplified version of the equilibrium part. She's asking about the dynamical part, which was separate.
That's exactly right.
These two are separate issues.
Well, except for the fact that this theory is aimed at trying to understand whether what kind of an Ising-like description of what's going on makes sense. The first part says, okay, let's assume that there's some sort of Ising-like scaling of the length and time scales.
Okay, it's
Right.
the same as this.
Then you say, all right, what kind of justification can you make? How can you get a piece of this that shows that there's some high? Can you let me talk through? Come on, Bobo. The question then is, all right, where could an Ising-like scaling of the length scales come out? What kind of a model? And that's where I introduce this two-state assumption, two-state clusters plus voids. And that clearly is based on an Ising-like idea, right? I write the field theory and I compute these isotherms, so to speak, for that. And I can make the isotherms agree, and it was not trivial, by the way. I can make them agree with the method. Basically, only the coupling constant.
J.
The J, yeah. No, those are all.
Yeah. So no,
There are not very many parameters at all. It's robust. I mean,
Could you just go back to the slide where you showed this calculation? Because
showed which?
the partition function. So where did I guess one before probably will be helpful.
Yeah.
So where is the polydispersity coming in?
The polydispersity determines J.
J.
And that's the one thing I have to do, and I have to say that as the polydispersity goes up, J goes down, and I plotted in the paper that I wrote what the J as a function of polydispersity was. That makes sense because I have these clusters in increasingly disordered places, and the coupling between them should get weaker. Okay. So look.
Where does the critical packing fraction come out of these equations?
Well, I didn't pay too much attention to that because I'm not getting all that close to it. The critical packing fraction occurs when eta equals 0, when I don't have any extra space between them. At least that's a critical packing fraction.
0 or 1?
No, eta equals 1. That's right. Eta equals 0 is when I'm the opposite.
When you compared those curves in the experiment, you varied eta and j? Or how did you?
No, because look. Yeah. What I do if I would make variations of m and I make variations of eta, and I minimize the free energy, so to speak, with respect to those things. And then I've done one.
At a fixed volume.
Well, yeah.
And then you're looking at P as a function of.
That's right. Yeah. I vary the entropy at a fixed volume. If that, or basically I take the free energy, understanding that it's the pressure over kT that is the Lagrange multiplier. And it's a trivial calculation. The one fiddle I've made is that if you look at here, and if you look at this one where does seem to be a dip in the curve, I can't get that dip with the mean field Ising exponent. I mean, it'll look like this, but it won't. It'll come up smoothly, but then you know that for 2 dimensions that the mean field Ising result with beta equals 1/2 is bad. Beta is really equal to about 1/10 or something. And so if you put that in, then this curve just drops into place.
And how would you, in this picture, interpret the psi6 correlation function? What's that correlation like in your picture?
In this model,
that's the correlation like they're measuring, right? The psi6.
That's right.
So how would I connect that psi6 to this?
Well, but look, I have these n plus ordering. And
why is it psi6? So you're saying
the n plus n minus are the numbers of hexatically ordered clusters, whether oriented one
No,
direction.
I thought it was the size of the cluster that's the correlation.
No, that's the number of clusters.
No. The length scale would give me the size of an hexatic cluster, right? If I look at the psi6
Now be careful. Now look, you're confusing a couple of things.
Okay, yeah, probably am.
What I want is to say that the clusters themselves are small groups of particles that have topological ordering, right?
Okay.
And
so the n plus correlation function would map onto your psi6
that's right.
correlation function.
Exactly right. And if you have an Ising model like this, then in fact what you know is you change the parameters, the temperature or the pressure or something, and you modify that correlation length. You can get it easily. That's essentially what I was saying. You can get it easily, from the mean field approximations.
It will diverge at some phi for you.
It will diverge in 2 dimensions. You're not doing a good job with the fluctuations, and rather than spend a lot of time doing a renormalization theory for this picture, I didn't bother doing that because it was.
No, that's what I said. So this will diverge at some volume.
Precisely. Well, if you like a volume or a pressure or a volume fraction is the more.
Hexatic has sort of an hexatic order. Why do you do 2 steps?
Well, because I know that when I'm below the transition, especially when I'm talking about a polydispersed system, that the hexatic topological correlations are getting weaker. That's why you need to what you need to express with that J.
But the psi6 is a continuous order parameter. Right? Psi6 is a scale, but it is a scalar, so I guess you could just.
I'm sorry.
Yeah, but
psi6 is a length. That's not.
No, psi6.
Oh, psi6. That's right. That's a continuous order parameter. Yeah.
Jim, I just want to ask a quick question because I'm a little confused. I normally think of sort of 2 states, STZs, 2-state systems as being places where there's less order in the system.
Yeah.
And I would have thought that this n plus n minus would be regions that are in between. In other words, there's sort of.
Don't think of these as STCs at all.
Okay. So you're saying that that the clusters that I'm imagining changing their orientation are these rigidly connected objects?
Yeah, to a first approximation.
Okay.
Okay, let me just say what my understanding of the discussion is going. So you sort of introduce this system as a way by which you might look at a hexatic correlation length, which Tanaka's result claim is a relevant static length or indicate is the relevant static length.
Yes.
But the calculation you've done doesn't really give you a handle on describing or hexatic order or to calculate the correlation length that corresponds to it. You've sort of made, that's part of your thinking in writing down an equation of state calculation, right?
Yeah, but look, you're right, Sri, that what I've done is I've said, look, it doesn't make much difference what the actual ordering variable is. And in fact, in 3 dimensions, it's not size 6. It's.
Okay, but you haven't shown us any calculation of a correlation length here that comes.
Well, no, but look, but what I've said is that look, I've written down an Ising Hamiltonian. Everybody knows how to do a correlation.
I understand, Jim. When you write down the Ising Hamiltonian, I still don't understand why a hexatic order parameter maps onto an Ising order parameter. I just don't get
it's
it.
not the look. It's not the same. Those are not the same order parameters.
I'll do it for the hexatic order.
It makes a mess if you try to do it like that.
Yeah, but when you compare it.
Look, if I try to do it with a hexatic order parameter, then what I'm getting is it's a rather different feature of the system. The hexatic,
no, but you are looking at that order parameter.
But that's what the experiment.
The experiments look at that order parameter, but then they look at what the correlations are. Look, there are various papers that are written. In fact, trying to remember which one, where they tried to make a field theory. I think, in fact, probably this is the way they do this, the exact solution for the zero. Of the monodispersed system, it gets even
but
that difficult.
Isn't that just Kosterlitz-Thallis?
Kosterlitz-Thallis is one of the early versions of that, and Kosterlitz-Thallis, however, is it doesn't work very well if you get away from the actual transition point. Here I want to say that the transition point, when I have a polydispersed system, even weakly polydispersed, doesn't look like the correlations that you want to get from Kosterlitz-Thallis. Kosterlitz-Thallis gives you this remarkably rapid divergence of the correlations as you get to the actual.
So isn't it an interesting question to ask how polydispersity changes the transition from?
Of course, that's exactly what I'm asking. I'm showing you.
So if you make the void smaller and smaller, will I get to Kosterlitz-Thallis?
Void smaller and smaller.
Or something. Is there a parameter in your which will drive me from Kosterlitz-Thallis to Ising?
In a way, it's the J.
That is the polydispersity. That can't be. Your J, tuning your J is not going to drive you to Kosterlitz-Thallis.
No, it's not on this because that's not the way. Look, let me put it another way. Okay, another way of thinking about it is that let's just have this picture in front of us, and you can see, for example, I didn't mark it, but here's a place where I have some sort of a transition. The thing comes up, and there's some sort of a kink in it, and that's Tanaka's data. And I can, by adjusting that J, I can get that solid curve.
All you adjust is J.
But yeah, I think that's all I adjusted there. I have to get the. I have to make sure that the volume coefficients turn out right. But we can look at that. That was not what was worrying me most when I first was trying to do things with this picture. Now, suppose that you try at a point like this, or even down here. Suppose you say, all right, I'm going to take this model, and it gives me in mean field theory some sort of a correlation length, which presumably seems to be diverging as I get to some sort of transition there, because it's an Ising model. Okay, and that's if I just use the Ising model, that's going to give me a wrong picture of this in detail. Because what I would do would be, I would start renormalizing it. I'd start making bigger clusters out of the smaller clusters. In principle, what I would do then is that I would recover the circular symmetry in the system, which I've broken by my approximation. But if I renormalize more and more, I recover the circular symmetry, and I will get back to something at least at zero polydispersity that is going to look like Kosterlitz thalamus. Okay? Now, so what I'm doing here is I'm saying, well, how come when you look way up in there somewhere and see something that looks like a diverging correlation line, it has Ising properties. Okay? And in order to have Ising properties, I have to somehow, what? So far, this is 2 dimensions, although he sees the Ising-like stuff in 3D too. And so does Delgado and company. So you have to allow me to be making some approximations in order to see, roughly speaking, am I in the right ballpark? And I will admit to you, look, I tried calculating this with various other assumptions, and it didn't work. And then all of a sudden this worked, and I thought, my goodness.
So your theory explains the pressure packing fraction dependence.
Explain is too strong a word, but yeah, it explains it on the basis of a model that is based on the Ising-like 2-state system, which will give me Ising-like exponents for correlation lengths.
So on that note, I think maybe we should break for lunch and then continue the discussion. Yeah. Thank you very much.
Very quick.